Welcome. The discipline of computer science faces a profound epistemological tension. It is the conflict between the mathematical certainty of the worst-case scenario and the empirical reality of the average case. Today, we explore how we justify our belief in algorithmic efficiency, moving from a paradigm of pessimism to one of realistic engagement with a stochastic universe.
Let us begin by addressing the crisis at the heart of algorithmic analysis. How do we define knowledge when dealing with infinite potential inputs, and is our traditional pessimism obscuring the truth?
In epistemology, we ask what justifies a belief. Traditional internalist computer science relies on deductive proofs, proving a worst-case bound based solely on the code logic. However, modern externalist thinking, known as computational reliabilism, argues that an algorithm is justified if it functions efficiently in its actual environment. It shifts our focus from the abstract logic of the code to the real-world distribution of inputs.
The Invariance Thesis states that all reasonable computers are polynomially equivalent. However, this broad equivalence can mask critical performance details. It abstracts away the polynomial gap between the constant time access, O of 1, of a random access machine and the linear movement, O of n, of a Turing machine. In performance engineering, this polynomial overhead is the difference between viable and useless.
To navigate this landscape, we use a specialized linguistic framework, asymptotic analysis. Let's dissect the tools we use to describe tractability and what they imply philosophically.
We rely on three primary descriptors to bound algorithmic growth. Big O establishes the asymptotic upper bound, acting as a ceiling on resource consumption. Conversely, Big Omega defines the asymptotic lower bound, setting a rigid floor. It asserts that a function grows at least as fast as a specific rate, often used to define the intrinsic hardness of a problem. Finally, Big Theta represents the ideal of precision, sandwiching the behavior strictly between the upper and lower limits.
Let's focus on Big O. Mathematically, it states that the function f of n is less than or equal to a constant times g of n. It answers the defensive question: if a malicious daemon constructs the input, will the system crash? In avionics or pacemakers, this worst-case guarantee is not just math. It is a mandatory safety certification.
However, notation hides reality. Consider the hidden constant. Quicksort has a worse theoretical complexity than merge sort, yet Quicksort is the industry standard. Why? Because its inner loop is cache efficient, making the constant factor c extremely small. In the average case, a millisecond times a small constant is far better than a millisecond times a large one.
We analyze algorithms through three lenses. The best case exploits benevolent structure. For example, TimSort detects sorted runs to achieve linear time. The worst case assumes an adversary. Paradoxically, that same sorted list is the worst possible input for a naive quicksort, degrading it to quadratic time. The average case assumes a stochastic stance, treating inputs as probabilistic signals, representing the true economic reality of computing.
The average case is statistically superior for general-purpose computing. We calculate the expected running time, t average of n, by summing the time of every input weighted by its probability, mu of x. This shifts our philosophy from defending against the impossible to optimizing for the probable.
The triumph of this approach is Quicksort. By assuming a random permutation of inputs, we prove that the average number of comparisons is approximately 1.39 times n log base 2 of n. It is only 39% above the theoretical perfection. This mathematical fact vindicates the use of a risky algorithm in production systems.
But what if the input isn't random? What if it has structure? This brings us to input variability and the concept of entropy. Standard analysis assumes a uniform distribution, but real data often follows Zipfian laws with heavy hitters. While a good hash function distributes keys evenly, the access pattern itself remains skewed. To optimize for this, we can use heuristics like move to front within collision chains. This ensures that the most frequently accessed items, the heavy hitters, are found instantly, rather than being buried deep in a linked list.
To bridge the gap between the pessimist and the realist, we use smoothed analysis. We allow the adversary to pick the worst input, but then we add a tiny amount of random noise, sigma. This simulates the measurement error inherent in the physical world. It proves that algorithms like simplex are efficient because their worst-case inputs are fragile singularities that vanish under the slightest perturbation.
We can visualize a spectrum. On the left, the worst case provides safety. In the middle, smoothed analysis provides robust efficiency. On the right, the average case reflects empirical reality. As we move right, we transition from mathematical logic to physical reliability.
In conclusion, the average is not a compromise. It is the most precise description of the reality we inhabit. By embracing input variability and distributional complexity, we move towards computational reliabilism, trusting algorithms not because they are perfect in a demonic world, but because they are robust in our own.